All right, welcome to chapter 10. We're going to continue the rotational motion discussion. So these first four sections of chapter 10, we're going to get through. So first of all, your book is going to prove a couple of formulas. I'm mainly going to just write down the results and talk about the results. If you want to see the details of the proofs, you can look, read this stuff over here on the left. So we're going to talk about the parallel axis theorem. We're going to talk about translational versus rotational kinetic energy, and just kind of a general fact that you can split total kinetic energy into these two pieces. And then we're really going to focus on rolling without slipping. So the combined translational and rotational motion and how to connect the two. And this is going to involve rolling without slipping. So actually, when you read this example problem over here on the right, this phrase seems pretty innocuous, rolling without slipping, but actually it's key to solving this problem, right? If it, well, not right, but you're gonna you'll agree with me by the end of the video, hopefully. Okay, so let's knock out these first couple sections first. So the parallel axis theorem. So first of all, your textbook just kind of reviews the previous chapter. And then states this theorem and then proves it. So we're going to jump straight to the stating of the theorem. Parallel axis theorem. So I'll write it down, talk about it a little bit, and then give a simple example of how you would use it. So the moment of inertia for a planar body about any axis is... I think he just says planar because he just proves it for planar, but it's actually more general than this. So if you had, you have some body, some rigid body, and suppose the pivot is, well, not just any pivot, but it has to be the center of mass. So suppose the center of mass is right here. Okay. And you went through a bunch of work to calculate the moment of inertia about some axis. So it could be any axis. It could be this one, could be this one. We don't know what that axis is. Suppose we happen to choose this one right here. Okay, so this is the axis through the center of mass. So it's a special one, right? It's not just any axis. Like this is a random axis that doesn't go through the center of mass. Axis through the center of mass. So for that axis through the center of mass, it has some moment of inertia that we're going to call ICM. It's the moment of inertia for some axis that goes through the center of mass. So what the parallel axis theorem says is that if you knew that moment of inertia, if you went through all that work calculating that, which it would be a lot of work for a random shape, and you wanted to know the moment of inertia for a new axis of rotation, that doesn't go through the center of mass, but an axis that's parallel to the other axis. So this is a new parallel axis of rotation. So notice how, just to emphasize that this center of mass, this is not a pivot point, right? We're rotating about this axis. So you have to imagine like this body, you could rotate around this thing, or you could rotate around this thing. So you have to imagine like the right-hand side of this body is going into the screen, and the left-hand side is coming out of the screen if it's rotating around this axis, right? Okay, so this is going to have some new moment of inertia. So what the parallel axis theorem says is that the moment of inertia for the new axis is the moment of inertia through the center of mass plus md squared, where d is the distance separating these two axes. Okay. So note that the term on the right-hand side is positive. Md squared is positive. So the moment of inertia for any axis that's not through the center of mass is going to be bigger than the moment of inertia through the center of mass. And this makes sense because the center of mass is sort of like the middle. It's a weighted average. It's the center of where all the mass is. So if you're summing up mr squared, the center mass would minimize that. If you have something far away from the center mass, the mass is going to be farther away from that axis versus the center mass. And by the way, the this d can be off of the object. Like in principle, you could have an axis over here, connect this rigid body with a very thin, negligible mass thing, and rotate it around this axis too. And you would use a d from this axis to the center of mass axis. So in other words, so your axis of rotation doesn't have to be on the body. You can still use the parallel axis there. Okay, let me give a quick example of this. So, example. So you know that a rod about the center of mass has moment of inertia 1/12 ml squared. Okay, so it's a uniformly distributed mass rod with total mass, capital M, and the whole length of the rod is L. Okay. So you could use the parallel axis theorem to prove something that we already know. So what's the moment of inertia about this axis? So actually, this is in our table of moments of inertia that we should have easily available because it comes up so often. So the moment of inertia about this new axis is the moment of inertia through the center of mass. So notice how this axis, this new one, is parallel to the old axis, to the piece that we already know. So we can do this plus m times d is going to be this distance. D is 1/2 the length of the rod. So L over 2. So m times d squared. So the moment of inertia of a rod about an axis that goes through an endpoint is 1/12 ml squared plus 1/4 ml squared. So 1/12 plus 1/4 is 1/3 ml squared. So actually, we've already seen that the result was 1/3 ml squared. But you can see how powerful the parallel axis theorem, because we didn't have to choose a point on the end. We could have chosen a point that's right here. So say we chose an axis that was L over 4 away from an end, and this was L over, not L over 3, 3/4 L. So if this is the case, then you would have I as ICM. You have to start with the center of mass one. So we can't just take the 1/3 ml squared and then add to it to get this one, right? This is actually going to have a lower moment of inertia than the 1/3 ml squared. So you have to start with the center of mass one, and then here you would add L over 4 squared. So it looks like this would be 1/12 plus 1/16 ml squared. Oh boy. This is 7/48, is that right? So you could write this one as 4/48, and then this one is 3/48, so this is 7/48. Kind of a gross number. So this is bigger than the 1/12 ml squared, but not quite as big as the 1/3 ml squared, so that makes sense. So you can see how powerful this is. You could do any, as long as you know the moment of inertia through the center of mass, you could do any, the moment of inertia pretty easily through any parallel axis. This is a pretty great result. Okay, so again, your book goes through this, and it's not terribly hard to go through. It just take a while for this video. Okay. Oof. Yeah, so you just got to be careful about like what you're defining to be the origin, etc. So blah blah blah. Okay, next result. So what your book does here is it talks about kinetic energy, and it says that the kinetic energy is 1/2 mv squared, and this is true. This is the total kinetic energy is 1/2 mv squared, pretending you're ignoring all rotation or anything. Okay. But it's nice to think about, to separate the motion into like the motion of the center of mass and then some rotation about the center of mass. Okay, and this is exactly what he says in this bottom equation right here. So this is VI. So what your book is doing, so the velocity of any particle is, so this is actually the same as the relative motion equation, but as applied to rotational bodies. So you've seen this before. This is like VAC equals VAB plus VBC. So this is just saying that the motion of any body, the motion of a particle, in some frame. So the general motion is the motion of the center of mass plus the motion of the particle about the center of mass. So this is nice because if you want to talk about a system, like the whole rigid body, you talk about the system as a whole, which is this first piece, and then any modification, if the particle is moving about that center of mass, then you're going to modify it with this term right here, the velocity about that center of mass. Motion of particle about the center of mass. So again, VAC equals VAB plus VBC. I guess, so written that way, it's like the particle about some, the motion of the particle in some frame is the velocity of the particle relative to the center of mass plus the velocity of the center of mass relative to the frame. So maybe the indices look a little shuffled here, but it's the same idea as what we've seen before. Okay, so your book writes that down and follows the logical consequence of that. So plugs that into the kinetic energy equation. Okay, it's just writing the speed in the frame. So this thing, 1/2 m this velocity squared, as a sum of those other two terms squared. And he shows that this cross term actually cancels out. So there's a little bit of discussion talking about why that cancels out. But the result is that you can take the total kinetic energy, and like how ugly that K looked. K total, the total kinetic energy, is a sum of two pieces. So it's the, so by the way, capital M is the total mass of the whole system. So I referred to a center mass of some system. Capital M is the total mass of the whole system. It's like your book replaces sum of lowercase m sub I is capital M. So the total kinetic energy is, you just ignore all rotation and just track where the center of mass is. So 1/2 mv squared. This is the translational kinetic energy. Plus, and then the other term is the rotational kinetic energy. So your book calls this KCM, the kinetic energy about the center of mass. So we'll also write this as K total is K translational plus K rotational. Okay, so we'll also write this as 1/2 m v translational squared, or I guess very rarely actually would I write the word translational there for velocity. Really, we would stick with center mass here. And then for rotational, we would do the 1/2 I omega squared that we talked about before. So the total kinetic energy you can split nicely into two pieces, the translational kinetic energy and the rotational kinetic energy. Okay? So it's a really nice way of splitting a complicated problem into two easier pieces, two pieces that you can actually manage. Okay. Okay, so your book goes on to discuss simultaneous translations and rotations. So what the heck does that mean? So let me give an example of this. Okay, so we can think about just translational motion, like purely translational motion and purely rotational motion before we try and piece them together. Rotational, there we go. Okay, translational versus rotational motion. Okay, so we're going to talk about a car, like a car's wheels. Okay. So to make this connection with this picture right here. So we'll come back to this picture, but we're working our way towards understanding that picture. So we're going to think about a car's tires, and let's just focus on one tire. We don't have to worry about the whole car. There's two sort of limits of what could happen. So the way I wrote it, I'm going to focus just on translational motion. Okay, so you could have a car where so there's no rotation, so this thing is not rotating, and the whole tire is moving with some center of mass velocity. So v center of mass. That means that this particle is moving v center of mass. That means this particle is moving at v center of mass. That means this particle is moving at v center of mass. Right? Every single particle here is moving with the same velocity. All particles moving at VCM. So the wheel would slip, right? You can imagine this could happen if you pretend you were driving and you just slammed on the brakes and you didn't have ABS or anything and the wheels locked up. So maybe there's a frictional force going on, but and maybe this thing is slowing down, the wheel is slowing down, but at any moment, every particle on the tire is moving at the same speed, and that speed is the speed of the center of mass. Okay, so this is like skidding. So imagine a car tire is skidding on the road. So the car tire locked up. The other limit, maybe you could try and pause it and think about what I'm going to draw on the right-hand side. You could probably guess this. The other limit of what could happen is purely rotational motion. Okay, so this is not moving, not translating. So if the first one was skidding, this one is like slipping on the ground. So there's no motion of the center. So the center is not moving. So this one has v equals 0. But the tire is rotating. So that means this particle is going this way, this particle is going this way, this particle is going this way, this particle is going this way. And remember, and we have this toolbox of rotational equations. And remember that the translational speed of any particle is omega times its distance away from the axis of rotation. So here the axis of rotation is at the very center of the wheel. And remember, because of this result here, it's nice to separate things into center mass motion and rotation about the center mass. So here we're looking at rotation about the center of mass. So the speed is proportional to our distance away from that center point. So that means this particle right here is moving at half of that maximum speed. This particle here is moving at half the maximum speed. If you look at one even closer, it's moving at 1/4 the maximum speed. So the speed is increasing linearly the farther you get away from the that center point. Okay. So here the particles are rotating about the center of mass. Particles rotating about the center of mass. Sorry. Okay, so there's one parameter that is describing how fast particles are moving. Okay, so the radius of the tire is fixed. So here the speed, the parameter is VCM, and here the parameter is omega, describing how fast the rotation is. So in principle, these two things are independent. So like, and we've used that fact in drawing these two pictures. So the fact that the car tire could skid means that you could have translational motion without rotational motion. And this car tire could just be rotating in place. So like, thinking about this scenario on the right here, this is kind of like a race car at the very beginning. So imagine someone slams on the accelerator and the car tire starts spinning like crazy and just the car's not accelerating, or for a short amount of time, it looks like the car doesn't move very much at all compared to the car tire rotation. So these two things are independent. There's one condition where you can relate these two. So if the tire is not slipping, if the wheel, I should say if the object, to keep this general, if the object is not slipping, then we can connect these two. Then these are related. And so now we can start to understand this picture. So if the tire's not slipping, that means that the velocity on the ground has to be equal to 0. So looking at this point on the bottom and this point on the bottom. So if you couldn't see where I just put a star, I'm looking at this point right here in both of the pictures. So at that point, notice how the translational motion's to the right, the rotational motion's to the left. And remember the way I labeled this, like let's use the VBC and the VAB. So the motion of the particle about the center of mass is VAB. So here VAB would be to the left, particle with respect to the center of mass. And then here, this is the velocity of the center of mass relative to the ground. So the no-slip condition says that the velocity of the center of mass with respect to the ground is 0. So I want to be careful about writing this because VCM is non-zero. But see, so if we were to add VBC plus VAB should be 0. So the magnitude of this thing and the magnitude of this thing should be the same if the wheel is not slipping on the ground. So the no-slip condition is that those two V's are the same. And looking at this, that means the radius of the wheel. So that's a special R, capital R. So this equation was true for any point on the wheel, and we left it general in terms of lowercase r. But on the edge of the wheel, that's going to be capital R. So these two things have to be related by V equals omega r. This is called the no-slip condition. So in other words, if the wheel is not slipping, you can connect the translational and the rotational motion. Okay, so see, this is exactly what this picture is saying. So this picture is actually combining the two pictures of what we just drew. So let's assume that the no-slip condition is true, and then look at the motion of the wheel in the frame of the ground. Okay, so in other words, we're just going to take these two pictures, and for any point on the wheel, we're going to add those two vectors. Add the velocity vector on the left and add the velocity vector on the right and see what we get out of it. Okay, so if the wheel's not slipping, so we already said that this point on the ground is not moving. So this one has V equals 0. This one is moving with some center of mass velocity, VCM. The top one is moving twice as fast. It's 2 VCM. Right, it's VCM from the translational motion, and then in the same exact direction, just for that point, they point in the same direction. For this point, the velocity of the particle about the center of mass is also to the right, and equal in magnitude to VCM because of the no-slip condition. This point is maybe a little more complicated. There's motion, there's a component of the velocity upwards from the rotational motion, and then also to the right from the translational motion. So this point is actually going up and to the right. And actually, because this component is VCM and this component is VCM, the magnitude of this is square root of 2 VCM. So that's not at all obvious, right? See, you can start to see the utility, how powerful thinking about it this way is. Because if someone just gave you a car tire and said how fast is like the top of the car tire moving, you'd be kind of at a loss for what that is, especially, a point like this. Where is it moving? How fast is it moving? Well, thinking about it this way, we know that it's actually down and to the right and moving at square root of 2 VCM. But how would we have known that without doing all this? So points in between, are going, so like along this line, this would be 1.5 VCM, this would be 0.5 VCM. It ranges from 0 to 2 VCM at the top right there. So I really like this picture in the book, but maybe it deserves a little bit more explanation of what ingredients go into that, translational and rotational motion. And the overall effect is this picture right here, when you combine the two using the no-slip condition. Okay. And actually, we're in a position to answer our question right here. So, by the way, I brought this up. Your book does that picture and then talks about the no-slip condition in the very next section, 10.4. This VCM equals omega r appears right here. But I thought it was more relevant to bring it up for that section in particular. Okay, so let's answer this question. A hollow sphere rolls without slipping. Now we know what that means, what we can do with that on a surface. What percentage of its total rotational, of its kinetic energy is rotational? Okay, so we're going to answer the original problem now. So we have a solid sphere. So imagine that all the mass is just on the edge of this sphere. So hollow, nothing on the inside. And this thing is rolling without slipping. Now they didn't tell us the center of mass velocity, but it's actually not, the way they phrase the question, it's actually not going to matter. All right, so we're going to introduce, we're just going to suppose that the center of mass is some value VCM. Okay, so we're going to, maybe I'll just assume VCM. So our final answer can't depend on VCM, but we're going to assume that the center of mass velocity is VCM. So because it's not slipping, the no slip condition tells us that VCM is also equal to omega r. Okay, so if we have an omega, we can replace it with VCM over r. So in other words, this right here. Okay, the total kinetic energy we learned before is a sum of the translational kinetic energy and the rotational kinetic energy. So the translational is 1/2, and I guess we're also assuming the total mass of the sphere is m. 1/2 m VCM squared. Maybe I'll be explicit here. This is k translational plus k rotational. And k translational is 1/2 m VCM squared. Now k rotational is 1/2 I. Remember this is the translational kinetic energy in the center mass frame. So we're going to use the moment of inertia about the center of mass. 1/2 I omega squared. So this is 1/2 m. We're just going to keep this term here and rewrite the second term. ICM, now this is in the table of moment of inertia values that you should maybe even have memorized. Like really, you should do enough problems. I don't know. I think you should have these memorized. We'll talk about this in class, whether you should actually have these memorized or not. But eventually you should know that this is 2/3 m r squared. Okay, so there are only about 5 objects that reappear over and over and over again in problems, and a hollow sphere is one of them. So if you're asking why isn't this 2/5 mr squared, that 2/5 is for a solid sphere. So if the mass was spread out over the whole interior of the sphere, then it would be 2/5. But because it's a hollow sphere, it's 2/3 mr squared. And for omega, and this is what allows us to do this problem, for omega we can relate that to VCM. So omega is VCM over r because it's not slipping. So this is 1/2 m VCM squared plus 1/2 times 2/3 is 1/3. And the r squareds are going to cancel here and here. So it's 1/3 m VCM squared. So the total kinetic energy is the sum of 1/2 and 1/3. It looks like that's 5/6 m VCM squared. Now, the original problem said what fraction of it is, I believe it was rotational. What percentage of its total kinetic energy is rotational? So if we take the rotational kinetic energy divided by the total kinetic energy, this will give us the fraction of the kinetic energy that's rotational. Looks like this was 1/3 m VCM squared divided by 5/6 m VCM squared. That's the total kinetic energy. 1/3 is 2/6, so it looks like this is 2/5 or 40%. So for our original problem, 40% of the total, and notice how the total mass canceled out, the total VCM canceled out. So we had to assume it to make some progress on the problem, but the problem was worded in a way that we didn't actually need to know what that value is. So it doesn't really matter what the speed is. It just matters that the thing wasn't slipping. So 40% of the total of the total kinetic energy is rotational, and that means 60% of it, of the total kinetic energy is translational. Okay. So the video is already 30 minutes. I'm going to wrap this up. I'll just mention that your book talks about conservation of energy. So you got to be careful now with conservation of energy problems. He talks about a ramp where you have a ball now with maybe some moment of inertia. So if you are going to find out how fast the ball is moving when it gets down to the bottom of the ramp, you can still use conservation of energy. Okay, so you have some initial potential energy, MGH, but you have to set MGH now equal to the total kinetic energy at the bottom. So this is K translational plus K rotational. And you have to know that the thing is not slipping in order to connect these two. If you want to combine those two into one kinetic energy, you're probably going to have to relate omega and VCM. And that's exactly what your book does in this problem. The author replaces VCM with omega R. So your book is assuming the no-slip condition in it, and you might want to read about it. So he talks about why that no-slip condition is guaranteed. But because of this, because there's some of that energy is taken up by the rotational kinetic energy, that means the center of mass velocity is not as big as it normally is. So your book points this out. The velocity of the center mass is not as big as it would have been had we ignored the rotational kinetic energy. And that's because some of that kinetic energy is taken up by the rotational motion. And how much of it is taken up by the rotational motion depends on the moment of inertia of the object. So there's a fun demonstration. We'll talk about this a little bit in class, or maybe this will be on your reading quiz. If you race some objects down the ramp like this, which one wins depends on the moment of inertia. The lower the moment of inertia, the smaller percentage of the kinetic energies in rotational motion, and that means the more of the kinetic energies in translational motion. So the smaller the I value, the faster it's moving by the end. The faster the translational center mass is moving. And so low I values win in this race down the ramp, and high I values lose. So like a ring where all the mass is at the end has the biggest moment of inertia, mr squared, that would be the slowest one to make it down the ramp. Okay, great. So onward to torque and angular momentum next video.